We are going to look at WPA in this video. WPA stands for Wi-Fi Protected Access. The purpose of WPA is to correct all the security flaws in WEP in web, and also it wants to reuse WEP hardware. Some of the which means that WEP was implemented on chips, and WPA can use existing WEP chips. Okay, so make existing web hardware support WPA. And moreover, WPA is compatible with the AA2.11i standard. So WPA was published in 2003 by the Wi-Fi Alliance. It was based on an early version. In particular, it's draft 3 of the IEEE AA2.11i standard. In particular, okay, so instead of using challenge response mechanism for authentication in web, WPA uses AA2.1x standard for authentication. And WPA also uses a better key generation and management. So there is a temporal key integrity protocol, TKIP. It uses microalgorithm for integrity check value. And it uses a new key structure to prevent message replace and decorrelate public initial vectors from weak arc4 keys. Okay, so that's what WPA was set out to do. All right, so WPA comes in two versions. One is for home and small office use, okay, for individual or for a small number of STAs in a home or in a small office. And it has another version which is called Enterprise WPA. This is for a large organization. It provides a secure WLANs for a large organization. So in particular, it uses an authentication server to authenticate users. So different user has different pre-shared secret keys with the AS, with the authentication server, in the form of passwords, usernames and passwords. Enterprise WPA also adopts AA2.1x port-based network access control protocol to authenticate STAs. So now let's look at AA2.1x authentication mechanism. So, so this is STA. This is an AP for a wireless network. It is connected to a wired network. On this wired network, it has AS, authentication server, and of course other network resources. So this is the data flow diagram. So STA sends a request to AP, request to join. AP then asks for the identity of STA. Okay, so which means that STA will sends in its identity, and excuse me, and with prior sequence. So STA then sends AP its identity and signature using the master key. So this is a share. So this master key share is shared with the AS. So that means STA and AP and AS, okay, has a shared secret, so that is in the form of password. Okay, so that means STA wants to join by sending in a request to AP. AP then asks for user's name and passwords, but AP is not doing the authentication. Instead, AP forwards the user's name and the password to AS. Okay, so then AS verifies the name and passwords. Okay, and then sends back to AP, indicates whether this STA is legit or not. And then the AP informs STA if STA is legitimate, then STA is allowed connection with the AP. Okay, for the key generation, temporal key, excuse me, this temporal key integrity protocol is for generating keys, TKIP key generation. And first, okay, after verifying the credentials of an STA, so AS first generates a 256-bit pairwise master key, PMK. Now they share, they have a pre-shared master key, which is in the form of password. When the password and the username and the passwords are authenticated, are verified, then AS will generate a pairwise master key. Okay, so AS sends this pairwise master key to AP using pre-shared secret key between AS and AP. Okay, so of course that means it's encrypted. When we say using a pre-shared secret key means this PMK is encrypted. Okay, using this pre-shared secret key. So AS, of course, can decrypt this message and get the PMK and encrypts this PMK again using a pre-shared secret key between STA and AP. Okay. So, so you want to get onto the AP, so you have a password and you have a username and a password, or you have a ID, you have a STA's ID and a password, and of course you also need authentication with the AS server. So usually at the user level. So for each new section, based on PNK and other information, TKIP generates 4 secret pairwise transient keys. So it's called PDK, and each of them is 128 bits long. So There are 4 of them. One is for data encryption. The other one is for data integrity check. Okay, data make key. So, oops. So message integrity check, and then you have a EAPOL key. This is for a protocol called extensible authentication protocol over LAN. So this is for encryption, okay, over LAN. And a message integrity check key for this protocol, EAPOL. Okay, so this is how these keys are. So how these transient keys are transmitted. So AP sends, okay, the following to STA. So this is the AP's nouns, okay, sequence number, and AP MAC address, the ID, okay, SSID, for instance. Then STA sends STA's nouns. So again, we know nouns is just a number generated to specify a particular message. Or so in this case, okay, so STA sends S nouns back. And then AP acknowledges STA, and then STA acknowledges AP, so then this connection is established, and then this PTK is sent over. All right. So for the integrity check value, instead of using CRC32, WPA uses the following algorithm, which uses a secret key. Okay, we now record that CRC32 doesn't use any secrets, so which of course is not good. In particular, here, WPA uses an algorithm called the microalgorithm to generate message integrity code. It creates a 64-bit message authentication code using a 64-bit secret key K. And so this K, then this K is divided into 2 halves, K0 and K1 of the same length. And this is the microalgorithm. So you can see here, so we're not going to go through this algorithm in detail, but you can see here that this function F is a substitution function, and you have this shift algorithm, you have this exclusive OR algorithm, you have swap algorithm. So as you can see, it is similar. Sorry, it is a implementation of Feistel cipher, and the operations are straightforward. Okay, and so of course, because it uses encryption, it is more secure. It is an encryption, so it is more secure than CRC32. But microalgorithm has its vulnerability. So the following is one. Such such vulnerability. So an attacker creates a message and attaches a 64-bit binary string as a MIC, okay, message integrity code, and tries to find the correct MIC without knowing the secret key. Okay, so needs to try all 2 to the 64th power possible keys to find the correct MIC. However, there is a more sophisticated algorithm, which is a differential cryptanalysis tricks or techniques, okay, which you only need to require 2 to the 29th try. So this is doable, okay? So this is much smaller than this number. So this attack is doable. Okay, so the solution to this attack is that is the following. When an STA detects, when an STA detects there are 2 failed forgeries within a second because it tries, right? So it need to try different mix, okay? So if within a second, there are 2 trials, which is unsuccessful, so then will be considered as forgeries, then as the STA deletes its keys, okay, and disengages with AP. Okay, so that means now it breaks itself off from WLAN. So that this attack cannot continue. Okay, so next is a key mixing scheme. So this mixing scheme, TKIP key mixing scheme or algorithm, is to generate a per frame key. Okay, so for each frame, you need to use a particular key for it. Remember, in WEP, for each frame you want to encrypt it, you always use the WEP key, but to indicate this key, to indicate that this particular key is for a particular frame, it uses an initial vector in WEP. Okay, of course, here it uses the same. The only thing here is that instead of a 24-bit initial vector used in WEP, it uses a 48-bit initial vector read. And that 48 bits is divided into 3 16-bit blocks, okay? Call it V2, V sub 2, V sub 1, V sub 0. And it consists of 2 mixing phases, okay? So as you can see, they just, this is a mixing scheme, just want to generate a per frame key so that you don't really have a direct, so just want to make the whole thing a lot more difficult for the attacker. So here you use, so this is a V2 from here, V1's from there, and this is so AT and this is KT. So AT is the 48-bit MAC address, okay, of the transmitter. And KT is a 128-bit data encryption of the transmitter. And PK2, okay, is a 128-bit per frame key for ARC4. Okay, so you generate PK1, PK1 goes in. So you first mix this up, okay, and then you put PK1 in there, you mix them up, and PK2 is the 128-bit per frame key, okay, rather than a simple per frame key in web, which is V concatenating K, K is a pre-shared web key. Okay, so this is a lot more sophisticated. And then it uses two X boxes, S0 and S1, to substitute a 16-bit string with a 16-bit string. Okay, so this is X boxes. So S box 1, S box 0. So now let's look at WPA encryption. So this is WEP encryption. You can think of this part as a chip made for web. Okay, so because in designing WPA, one of the objectives is to use any existing WEP hardware. Okay, so think of it as a chip for WEP. So for WEP encryption. So as we know, WEP encryption, it takes a frame, and then it also takes a WE key. Okay. And then you use ARC4 to increment, to generate R4 on the 24-bit initial vector followed by a web key. Now here it uses 104 web key. So the ARC4 generates a sequence of subkeys. So for each of the frame, you use one of the subkeys in the sequence. Okay, so that's what WEP. Okay, so we already discussed this in the previous video. Now, the key, the web key or per frame key is done through the mixing scheme we talked about earlier. So it has the source MAC address. You have the source encryption key goes in. V2, V1, and V0. This is a 48-bit initial vector. So it goes in mixing phase 1. The input goes in here. The source encryption key goes in there. Now you get V0 goes in. You mix them up. Then it generates, okay, 128-bit per frame key. So 24 bits of them is used as the initial vector. The rest is the web key. So then you can use the existing WEP chip. Okay, so then it comes out at encryption. So this encryption is on a frame. Okay. And now let's look at the integrity check. It uses Michael's algorithm. So it takes a 64-bit make key to generate a integrity check value. Okay, so this is a frame, but then depending on, because you're adding something in here, you're adding something in here, so it may need further fragmentation, but nevertheless it comes out. So this is one frame for this web encryption. That already includes a Michael integrity check value. So it comes in here. Okay, so finally it goes into this web encryption. Then you get FI, because this FI already has this integrity check value. and CRC32FI because you are using web encryption. You put the initial vector here, and then you get a new, you get a MPDU frame, okay, you send out. So there's a map header, the initial vector, okay, W2, W1. This is the IV here, and so you send this one out. Okay, so how secure is WPA? Of course, WPA was devised to correct all security flaws in WEP. Hence, of course, it is a lot better, much better than WEP. But it is also, WPA is vulnerable to denial of service attack. So the idea then is the following. So let's say after computing the message integrity code of M, WPA encrypts fragments, okay? M, and then ICV integrity check value of M, right? So this is, so this part, it uses Michael's algorithm, so this part. So then it generates a fragment. So it has this fragment. So then it becomes F1 up to F2. So that's what WPA does. So then for each such fragment, WPA needs to generate a 48-bit initial vector to create a WEP initial vector and WEP key. So this is a per frame key, okay? So each of these F sub I will get a new VI and a new KI, so capital KI as a web key. Again, this is what WPA does. So the problem here is this initial vector is transmitted in plain text. So to launch a denial of service attack, the attacker may intercept a MAC and MAC frame and replace the initial vector by, replace this initial vector with a larger value. So in other words, when this initial vector becomes different, the receiving side can no longer decrypt the receiving frames correctly, which resulting in dropping that frame. So if all of these F1, F2, blah, blah, blah are dropped at the receiving end, then of course it is equivalent to denial of service, okay? So once again, because now it has this larger value, okay? It says a larger value, then legitimate MAC frame arrives later will be rejected because this initial vector has been used. Or another, and so that's one. And then the other one is it results in an incorrect decryption, okay? So then both of these will result in a denial of service. Okay, so that is the end of this video. In the next video, we are going to look at WPA 2, which is a much stronger security protocol.